Now we are into the surface roughness in machining. Till now what we have studied is surface roughness, lubrication in machining and all those things. Whenever I am talking about surface roughness in metal cutting, I am more inclined towards what is the surface roughness in metal cutting. Okay, so till now in the previous class what we have studied is what is surface roughness, how do you define the surface roughness, what is centerline average value, what is RMS value, what is maximum peak to minimum value and all these things. This is the introduction to surface roughness, as the surface roughness is one of the most important responses that we take out from the machining experiments. Okay, so we all study lubrication in machining, types of lubrication in tribology and machining, introduction to surface. That is what I was telling. How we measure the surface roughness, profilometers, non-contact surface profilometers, and experimental techniques too, and representation of surface roughness and texture. These are all we have studied in the previous class. Okay, so now we will move into exclusively what is the surface roughness in machining pertaining to this particular course. Okay. So the surface morphology and the surface roughness. So surface roughness is one parameter of the surface morphology. Morphology will tell you not only the surface roughness, there is any waviness, there is any profile are there and all those things. Okay. So for example, if you see the surface morphology of the cutting tool, the machined, this is you have already seen, but from the angle of surface roughness. Previously you have seen this was a sticking region and sliding region as the tribological aspects. Now if you see your perspective of looking now in the surface roughness, how do you represent the surface roughness? Assume that I want to measure the surface roughness of the sticking zone. What I will do is I will just take the surface, just I plot a line like this and I will take the surface roughness. Or if I want to take across from the cutting edge, so I will take like this. Okay. So now that you will get in the form of surface roughness. So similarly in this, if you take in the region of this one, sliding region, you will get the profile like this, because if you see a flat region is there in this. Okay. So gradually it is going to tending to the parent material. That's why this is how we are looking from the surface roughness point of view. Okay. Okay. So now what are the parameters or input conditions that will affect the surface roughness? So what I am going to show is a fishbone diagram of surface roughness in the machining. So how the surface roughness will affect by various enormous input conditions that are there in the machining. So if you can see the surface roughness is what my output response is. Okay, there is a difference between parameter and response. If I am saying a input parameter, that means that I can vary it, because I am the person who is operating this machine. I can vary. If the feed rate is an input parameter means I can vary. Okay, the responses, when I talk about the surface roughness is a response. That means that I cannot control it, because it is an output response. Only I can take it. I cannot change it. However, I can get different output by changing different input parameter. Okay, so response is what I will get and input is what I will give. That's why whenever I speak about parameter, that means that are controllable things, and responses means what I am going to get. Okay, surface roughness is for me a response. Okay. If you see the machining parameters, the first I will take the machining parameters. The machining parameters are like cutting speed is one of the most important, feed rate, depth of cut, and the tool angles like rake angle, flank angle and all those things, step overs, and the type of cutting fluids and process kinematics, whether you are holding it properly or not. These are the major important input parameters. Normally most of the researchers will vary. Okay. So the cutting phenomena, whether it is acceleration, phenomena is there, whether vibrations are there, the chip formation you can see, and the friction in cutting zone and cutting force variations. Okay, these are the other things that normally mostly people won't touch this. However, the design people who do design of these machine elements or the machine tools normally thinks about if I am giving these input parameters, they will measure the vibrations, forces and the chip formation as an output parameters. Okay. However, the surface finish also vary with these intermediate responses. So, if you see the workpiece properties, the workpiece diameter, workpiece length and workpiece hardness. So, these are the another input parameters normally one can work is how much diameter. If my diameter increases, if the constant RPM, if I am using, if the diameter of workpiece increases, what will happen? My cutting velocity goes up. Okay, pi d n by 60. If you take that one, d is function and n is also a function. So, if my diameter increases, my cutting velocity will increase. So, workpiece hardness, if hardness goes up, I will take some of the glimpse of advanced machining processes where I will talk about hard machining. So, hard machining means if you are working with much harder workpiece material, that is called what? So, that is one of the studies that can take place here. Cutting tool properties is another parameter that one can vary, that is the tool material, whether it is a HSS, CBM, cermet or something, tool shape, whether the positive or negative, whether the nuts are there or not on the tool, and nose radius, whether I am going to use 0.4 or 0.8. For example, if you take a carbide tool TPUN 160308, okay, so that means the last one represents normally what is the nose radius. Okay, so in case of 160304, 160308, normally 0.4 is the nose radius. In other case 0.8, where 08 is there, the nose radius is about 0.8 nose radius. Okay, so these are all the input parameters that will influence. So this is the completely shows how these parameters influence my surface roughness. So it is not so easy to control all these things. This is independent parameters, but in a machining system, these are all combined, and there will be a combined effect also on the surface roughness. Okay, not only this individual, you will have a combined effect. Okay, the surface morphology of the workpiece. If you see the surface morphology of the workpiece, so if I am doing metal cutting, assume that this is a tool holder and this is the tool. If I am cutting my machining process, depth of cut is there and feed is there. Whatever we are seeing here, this if you see these things, anyhow I will show you a scanning electron microscope. This is the SEM image. I will explain you what is a SEM and all those things in upcoming slides. SEM refers to scanning electron microscopy. If I take a part of this one, if I cut using a precision saw and I place in a scanning electron microscopy, being a metal, there is no requirement of you for the gold coating and all those things. So you will get this type of variation. If I want to represent, normally for a simplicity's sake, the surface roughness looks like this in a turning process. These are nothing but the feed marks. So till now, if I say after my statement that these are feed marks, that means that most influencing input parameter in the machining conditions are feed rate. Okay, since these are the feed marks, feed is going to take part in a major to decide the surface roughness. Okay, so surface morphology, if you see, nose radius is also a important parameter to decide surface roughness. Okay, let me see. So this is the equation where RA is equivalent to F square by 8R, where F is nothing but feet and tool nose radius. Okay, if you see this picture, if my feed increases, what will happen? Surface roughness is proportional to feet square or feet. Okay, surface roughness is inversely proportional to nose radius. Okay, this one. How? Just now I was telling you that if there are two tools whose nose radius is one is 0.4, another one is 0.8. Just time I was telling TPUN 160304, 160308. Assume that a tool nose radius equivalent to 0.4, another case R equivalent to 0.8. In these conditions, this is the nose radius. Okay, this is going to replicate on my workpiece. So if my nose radius is low, what will happen? It will come like this. Okay, so what I am going to get? I am going to get the surface finish of approximately the, if I remove all these things, if I am going to get, if my nose radius increases, what will happen? This is my nose radius. Okay, if I remove these things, what will happen? I will get a better surface roughness. That means that my surface roughness RA value is going to decrease with respect to nose radius. Okay, so that is why I am telling your RA is inversely proportional to your nose radius. That doesn't mean that you have to go for very high nose radiuses. If you go for very high nose radiuses, there will be a problem of chattering and all those things. So always you should strike a balance between your nose radius as well as your surface finish what you require. Okay. Okay, now if you see, the surface roughness always follows the equation. Just now I was telling you that the surface roughness RA equal to F square by 8R. Do you think always this follows? Maybe, may not be. Let's see what will happen. Okay, so there will be the conditions where this may not be 100% true. Up to certain level it is true. Up to certain percent it may not true in case of built up edge formation. So my F square by 8R normally stands when there is a assumption that it is a continuous chip, there is no built up edge formation and all those things. If the built up edge formation is there, the surface roughness that you are going to get on the final product will be completely rough. So if you increase the feed, obviously it will increase. At the same time, your built up edge that is forming on the surface is also influences the surface roughness. Okay. So these are the built up edge fragments that are taking part on the workpiece. If that takes place, metallurgy will change as well as surface morphology will change. That means that our surface roughness will be changed. Okay. Now, I was talking about what is surface morphology, many times what is surface topography, what is surface metallurgy and all those things. In a metal cutting operation, you may be a PhD student, so you are well acquainted with the machining process, but what is the quality of the product that you got it, that you have to always characterize. For that purpose, I will just give you some introduction about how to check the surface morphology. So the first one is scanning electron microscopy, how the scanning electron microscopy characterizes our the surface. Okay. So if you see this one, you have an electron gun where electron beam emits, anode will be there, magnetic lens will be there to focus, and at last you will have a back scattered electron detector is there, and the stage is there where you just place your workpiece. You just place your workpiece on top of it. Normally you will get the electrons which will be detected basically. So what are the electrons that are detected? See, there are various type of electrons that are detected, among which there are three major things. One is X-ray photons will be detected, secondary electrons will be detected, which we are mostly worried about, and backscattered electrons we are worried about. Okay. These are the three things which normally we want as a mechanical engineer. But if you, the metallurgy people, material science people, they may go in deep of this knowledge. But however, for the introduction of this course, I guess this much is sufficient enough. So secondary electrons, from here the secondary electrons are captured and the detector will be there, it will detect. Backscattered electrons will come up to this one. These backscattered electrons are slightly bigger, and if you just bombard it and it will go to the detector of the backscattered electrons, and the X-rays will be there to detect the elemental analysis. So most of the time mechanical engineers have a slight difference, because backscattered imaging as well as the secondary electrons imaging are the two types of imaging. So what will be the difference? So for a BTech students or the basic people who are working on the characterization of the surfaces in a mechanical engineers, you may have some of the doubts. Okay, so if one can understand between the backscattered image as well as secondary electrons image, you will be used this technology for choosing which type of image I want after doing my machining operation. Okay, if you see the backscattered image, just if you see there are the aluminum and copper, two phases are there in an alloy. Larger atoms are lot stronger and compared to the light atoms. This number of backscattered electrons reaching to the detector proportional to their Z number, okay, that is valency number. Depend on the number of backscattered electrons, the atomic number helps to distinguish within different phases, providing the image. And what I want to tell is the backscattered image helps you in terms of differentiating the phases. If I have an alloy, okay, if I am doing a machining on an alloy where copper and aluminum is a part, if my surface is there, whenever I focus, if I want to check what are the phases are available on the surface, I should take the image which is backscattered image, so that you can differentiate aluminum, you can differentiate copper. Okay, my intention is to check the phases, then I have to. But backscattered image also give surface topography. Okay, it also gives surface topography if but conditions are there. The quality of this may not be superior to the secondary electrons image. Okay, if your thing is to find the element, I mean to say the phases, sorry, not the elements, it is the phases, then you should go for always backscattered image when you are doing your characterization using scanning electron microscopy. Nowadays, field enhanced scanning electron microscopies are also there, which go beyond what the scanning electron microscopies nowadays are doing. Okay, if at all I want to know about the surface morphology, then you should go for secondary electrons. In contrast, secondary electrons originate from the surface or near surface of the sample. Okay, these electrons are emitting. If you would have seen clearly in the previous slide where I have shown the scanning electron microscopy, if you see here, so the secondary electrons are coming from the surface. If you see, the secondary electrons are coming from the top. That means that surface topography will be the better one. Okay, so there are reactions between primary electron beam and the sample have lower energy and the backscattered electron than the backscattered electrons. Okay, just I will give you some glimpse. Okay, so if you see figure A, this is the full backscattered image. I am talking about the image of particular location on a leaf. It is taken from the Wikipedia, acknowledged to the Wikipedia. Just I want to differentiate between what is the backscattered image quality, what is the secondary electron image quality. Okay, for that purpose, the first A, this is the image which I have taken, which is a full backscattered image. If I want to convert this full backscattered image surface topographically, The final image that I am going to get is this one, that is B. But if I locate the same area and if I am taking the image from the same area using secondary electrons, okay, electrons, this is the topography. You can clearly differentiate between the pictures between A, B and C. That's why the understanding what a mechanical engineer, we may not be a very good at the metallurgical aspects, but whenever you are taking your pictures, you should be cautious to know what you want. If you know what you want, half of the problem is solved. So you can go ahead with this one and you can take. Okay. So what you understood from this 4 slides of scanning electron microscopy is, if I want the faces, I should go for backscattered image. If I want the surface morphology or the topography which is there on the surface, I should go for secondary electrons imaging. Okay. Hope you understand. Okay. Machined workpiece surface morphology. If I want to see the machine surface morphology, okay, this is the surface. If I am taking a secondary electrons image, and this is taken from a micro turning process. It is not normal turning process. It is taken from a micro turning, and you can also see the feed marks. So the feed marks are varied. If you see the feed mark here, if you see the feed marks here, there is slightly difference is there. So this is all depend on your cutting edge quality. If you are maintaining the cutting edge quality, you will get uniform. Otherwise, you will get lot of problems. These problems may be because of material defects in the workpiece, maybe the cutting edge problems, or if you are not supplying cutting fluid properly, this type of problems will come. So you can also see the material side flow. Normally, whenever you see the merchant theorem, you assume that there is no side flow, but practically most of the times you will have the side flow in the ductile materials. Okay, so you can see these are the feed marks. If at all I will take a cut from here and you just put a slab on it, but these pictures are different from this one. So for you, for the better understanding of the students, the pictures are taken from the Google source, and we are thankful for the authors who have posted it on the Google or published their work. Okay, so the tool Rake surface morphology, just I want to say you that till now we have seen secondary electrons, how it is affecting, and backscattered affecting. Now X-rays. So I was telling you that X-rays, how it will help you. Okay, so if at all I want to check this analysis, also I want to give you some glimpse of tribological aspects. For that purpose, flood cooling and minimum quantity cutting fluid, that is called minimum quantity lubrication type of things, is tested at our laboratory, wherein you can see that the secondary electrons image is taken here, and where you can see the sticking region and at the materials also. Now this is the flood cooling, and this is the MQCF with mineral oil. Normally we also tested with some of the advanced cutting fluids, that is called bio-cutting fluids, where we have done with the bio-cutting fluids of flood cooling as well as MQCF. That is clearly shown. What I want to show here is the scanning electron microscopy pictorial image of cutting tool. Okay, so you can see the sticking and sliding regions. If you are going to increase, if you see this particular picture, this is a sticking and sliding region, but if you are going to in the flood cooling, in minimum quantity cutting fluid application where high pressure is there and forced convection is there, which is better in terms of heat extraction, you will have a very less amount of tool wear. Okay, so if you see from the tool wear, it's the picture is you are seeing at the tool wear. If I am seeing from the scanning electron microscopy perspective, I can see from the both. Okay, this is the sticking region and this is a sliding region. Now for this type of things, how to check the elemental mapping. Okay, so this is the area for the same tool. How my X-rays, already you have seen backscattered and secondary electrons, now X-rays. So how the X-rays will help me? X-rays will help me in detecting what are the elements. Okay, backscattered will give me the phases, here it will give me what are the elements. For example, in this tool, this is a tungsten carbide tool, wherein the slightly tool is adhered by the workpiece material, that is called a slightly built up edge formation is there, and I want to check whether this particular area where white area is there is iron is there or not. That means that if I am metal cutting with respect to the stainless steel, or normally what we have done is a SS316L, I think. So if I am doing a stainless steel where Fe based material is there or not. So you can check if I am doing a point analysis at this point where we have specified, it is shows maximum amount of iron. That means this particular portion contains lot of iron. That means there is a adhesion by the chip material on the tool surface. So I confirm by using electrons bombardment of scanning electron microscopy by EDAX analysis. That means that elemental diagnosis analysis. And tungsten carbide anyhow is there, and molybdenum is a binder. Material will be there, cobalt will be there. And if at all I want to check a particular portion of any material, normally this is the image that we have taken from the cutting tool, which is textured basically, where we have a wicker hardness indentation is there, which is micro texturing is there, wherein the solid lubricant is filled. So solid lubricant is MOS2. So you can clearly see elemental mapping, iron, always iron is there on the surface. At the same time molybdenum is there, and at the same time sulfur also is there. Okay. So this is how you can map the elements, where these red spots are there, those are belongs to iron. This is molybdenum, yellow spots are molybdenum, and these orange ones are sulfur. Okay. So this is how you can detect the elements. Okay. This is about the scanning electron microscopy. Now we are moving to transmission electron microscopy. This is another way of checking in depth analysis. Okay. Whenever I am doing the machining process where the temperature is very high, what will happen? The grain boundaries will change. That means that the particle of that material may enlarge. How to check the grain boundaries and all those things? Because in scanning electron microscopy, my sample is very big, and if I want to inject and want to check the grain boundaries, it may not be possible. For this purpose, the first and foremost difficult situation or difficult work is that sample preparation. You have to make the sample so thin so that the transmission will take place across the sample. Okay. So the transmission electron microscopy, where the electrons will be moved and transmitted through the sample. I said the sample should be very thin sample so that the electrons will pass through and give the projected image. Okay. How the image look like? If you just see, this is also taken from the internet. So you can see the grain boundaries and all those things, grain structure and all those things. This you may not get in the scanning electron microscopy, because you need to pass through transmission. It has to transmit through that. If it can pass through the sample, then only it can give the image. That is what the transmission electron microscopy gives. Okay. So the application of this one, as I said, if I want to do the machining where the temperature is very high, whether parent material grain is some X size, whether the X size is still there or not after the machining on the surface. So it may have increased by some nanometers or Armstrong. Okay, or it is not increased. For that purpose, transmission electron microscopy will be used, whether it is still in the crystalline region or whether it is moved to amorphous region how the chip look like, and all those things we will see. If you see the chip, okay, so chip will have different zones. One is a free end, another one is a machined end. If you see the both ends, if you see the this region where you do, this is called seed graph. Normally, if you see the B, now B shows the amorphous nature and the C shows crystalline as well as amorphous. If I am looking at this one, sad pattern of this one, so you can check one case, the machining region or the machining side, you will have the amorphous nature. On the free end side, you can see the crystalline plus amorphous nature. So this can be detected by SAD images. And you can also see the machined surfaces. If at all, only thing is that I have to prepare the sample accordingly. If I cannot prepare, where my beam cannot transmit across the sample, you cannot take it. So you have to take the machined surface and just glue it and all those things. You can see the micro cracks, dislocations and all those things. If at all I want to check the surface metallurgical aspects, you have to go for the elemental analysis of SEM, and partially you have to go for the TEM analysis also. Okay, this is the another area. Being some of the students may be from bachelors, some of the students may be starting of the masters. This will help you in a great way to characterize your BTP samples or MTech samples which you are doing for your term projects or MTP projects, or this one in small institutions. If these facilities may not be there, so this, once you got this knowledge, you can search around your locality. If this characterization facilities are there, you can utilize the services and you can do good research work. That is what my motivation to explain to you for the manufacturing students. Okay, I was telling you the lay. Lay is nothing but predominant direction of the surface roughness. So if you see the horizontal, and anyhow I will come, because the lay I am ending the surface roughness here itself. So I am not coming into the next zone. So milling, grinding, lapping and all those things, the predominant direction. Horizontal milling, you will have a particular lay. Lay is nothing but predominant direction of surface. Vertical milling, you will have a lay like this. Turning operation, you will have a feed marks. So grinding operation, you have a straight line, because always you have a grinding wheel that will rotate tangentially to the workpiece. And normally the lapping process, the particles are freely moving. In that circumstances, the particles have independent to move in any direction. However, most of the times it will be in the direction of the motion of the lap. Okay, so this is about the lay, that is predominant direction of surface roughness. So you are talking about the big spectrum of surface roughness. Then it will be like this. So now we will move to the material removal rate. See, many mathematical models are there out and all those things. I am not going into the complete mathematics. As I said, there is a separate course floated by many other senior most faculty where you can study the mathematics aspects and material removal. There are standard textbooks also. It's very simple. How do you calculate and all those things. Just I will give you some introduction and I will move on to the machinability aspects. Okay, till now we have studied all these things, and now we are going into the material removal rate in turning operation, single point cutting tool. Okay, so then we followed by the machinability. Okay, so why we have to study the material removal rate in conventional machining? Why not in polishing process, such as lapping, honing, some other advanced finishing processes and all those things. Okay, why we want to calculate? The process itself is called a machining process. The machining process and the finishing process difference is, my machining process means how much material I am removing. I am worried about what is the volume of the material that I am removing. In a polishing process, I am not worried about how much material I am removing from the workpiece. I should look at what is my final output in terms of surface finish. Okay, so if my surface finish is 50 nanometers, that is what my requirement is for the finishing or the polishing process. Whether I remove 1 mm or 1 micron thickness or doesn't matter for me. In a material removal process, that means that conventional machining process, I worry about the material removal, because if I want to do the turning operation and bring a workpiece from 80 mm to 75 mm, I worry about that thickness material removal. I don't worry about the surface finish. Still, I worry about surface finish, but my major concern is material removal. Okay, that is the difference between a machining process and a finishing process or a polishing process. Here, in a machining process, how much material I removed; in a finishing process, what is the surface roughness that I got. Okay, that is what I am telling here. That is how much material I am removing is a concern. Here, what is the final surface roughness is a concern. So, material removal, if you see it, it's very simple. Whatever the thing, material removal in metal cutting indicates the volume of the chips being removed. Okay, volume removed per unit time. Okay, so normally volume removed is LW and T naught, whereas T naught is nothing but my uncut thickness, W is nothing but my depth of cut, and L is nothing but my length. So you can write time equal to length of cut by the velocity, cutting velocity. So if you can calculate this, normally you will end up with this one. Okay. If you talk in terms of input parameters, it will be like this. Okay. So where you know all the input parameters, which is cutting velocity, but you know cutting velocity you can calculate from the pi dn by 60. You can calculate the cutting velocity, where the input parameter is RPM, that is a rotational velocity of the workpiece. D is the diameter, and other things are known to you. Okay, this is the only thing that you are calculating. However, these two are input conditions apart from your feed and depth of cut. Okay, so total input parameters is diameter and the RPM, rotations per minute. If you know all these things, you can calculate your material removal rate. Okay, so that is what is given here. Okay, so I just divided the cutting velocity also into input parameters. Now we will move to machinability. Okay, the machinability is nothing but ease of machining. How easily I am going to machine my workpiece is nothing but the machinability. Okay, given material may be anything to me, whether I have machined it with easy or not, is what the machinability. That means ease which material can be machined. Machinability depend on physical properties of the cutting conditions and the cutting conditions. Okay. Also, machinability can be expressed in the percent of normalized value. These are some of the standards that one can follow. Machinability is a relative statement. Okay. So when it is stated that material A is more machinable than material B, it is I said no, it is a relative statement. Whether I have two materials, assume that I have a mild steel in one hand and on the other side I have a silicon carbide. So which is easy? Basically, with a common, if you are a machining engineer or a basic metal cutting is known to you, you can obviously say that mild steel is much easier to cut. Okay, why you say? You are talking about the relative with respect to the silicon carbide. Okay, so it's always relative. So machinability is always material A having a longer tool life compared to B, then you can say that material A is more easy to machine. Material A require roll cutting forces and power compared to B, then I can say material A is easily machinable, or the machinability of material A is good. Material A is providing better surface finish compared to B2B. In this condition also, the three conditions or individual conditions, if any one satisfies, that means that my material A is much better machinability compared to material B. Okay, this is the relatively statement. And the factors affecting the machinability are tool materials, feeds and speeds, cutting fluids, and rigidity of the tool holding device. How rigidly I am holding. If it is not hold properly, it may deflect. So if it deflect, so my machining conditions completely will destroy the microstructure that I am going to get on the surface, grain size of the machined surface, heat condition, chemical composition, fabrication methods, hardness, yield and tensile strength of the workpiece. Okay, many conditions will decides in fact the machinability. If it is very hard, it is very difficult to machine. Okay, you have to find some alternative solution to make the machining of that particular material is easy. So that is called machinability. So if you are going to get a good product with less forces and better surface finish for a particular material, as you have seen, with easy, that means that that particular material is easy. If you are a manufacturing engineer in certain company, if you think if certain customer comes and asks you to machine this type of materials, you have to see this machinability, whether it is easy and whether it is capable for our existing machines and all those things. Okay, if you see the tool rake angle versus cutting force, normally the tool rake angle, if it increases, its sharpness increases and the forces obviously will goes down. Okay, so what is the tool rake angle that I have to use for particular cutting of this material? Okay, so clearance angle also not play much role, it will rub against the final product. So obviously you should take care. I also said that clearance angle is nothing but the flank angle. So if you see the machinability rating, the speed of the machining of the work are 60 minutes of tool life to the speed of machining of the standard material for 60 minutes of tool life. Normally you decide machinability rating by this equation. At the same time, if you see particular material cutting velocity 60 and 100, if you are seeing standard material and specimen material, it will have at 60 minutes. Okay, so my specimen material will have 60 to 60 for the same specimen. How about the standard material? It will have you can go up to the cutting velocity 100. Okay, so for the 60 minutes, as 1 hour is my tool life condition for this one. Okay, if you see the different materials, the ceramic tools, sintered carbides and HSS, if I am taking the 1 hour as my tool life, or if I want to check for the particular cutting velocity, I can say, I can just drop, this is what the cutting velocity, assume that this X is the cutting velocity that I want. So HSS has its own tool life and ceramic material and sintered carbides. So you can draw here and you can show or you can identify what is the tool life. So this will tell the machinability of my particular tools. Okay, so this is about the machinability. So again, if you see the machinability, normally output responses, how I will look at is surface roughness of the machine part, whether I am getting a good surface roughness, tool life for that particular material. If I am having a better tool life, that is that workpiece material machining is machinability is easy. Force and power requirements, power requirement should be low if the forces are low. So forces experiencing during machining of this material should be low. And chip control, if I can control the chip easily, like there is no entanglement there itself and all those things. If it is a discontinuous is there by using a chip breaker and all those. Okay, machinability rating, if you see the among all these four, tool life and surface roughness are the most important factors that will decide the machinability of that particular material. Okay, so this is the condition for most of the companies, or whenever you are taking a research, you should look into it. I should get on a product better surface roughness with high tool life. If I am getting, you go for it. and you choose that particular workpiece material and tool material combination. Just machinability rating, just you have seen, if the T60 minutes standard material AISI 1112 steel given, normally if the rating is 100, this steel should be machined at a speed of 100 feet per minute. Normally the textbook which we followed is a American one, so abroad one. So here it is taken feet for the tool life of 60 minutes. This is what the machinability rating. Okay. So the final thing that I am going to talk about is machinability whenever you are talking about the ceramic materials. Ceramic materials are brittle material like glass. If I want to machine a glass, what will happen? If the forces are very high, it will break into pieces. So how do you overcome it? So for the purpose, there is called thermally assisted machining, which I have already talked to you, and I am going to elaborately talk at the end, where I am going to talk about advances in machining processes. Just I will talk, if the ceramic is there, just I bombard a thermal, that is means laser, I make the ceramic material softer, then I will cut using a single point cutting tool. Okay. So the laser is falling here. If you see here, laser is falling and the single point cutting tool is turning on. So this is called ductile regime machining of brittle materials. Okay. What do you mean? Ductile regime machining of brittle materials. Material is brittle, you are heating, bringing into the ductile mode, making it soft. Ductile mode means making it soft. Now you are removing. What are the advantages that you are going to get? If you see the advantages, lower cutting forces because it is softer material, tool life will increase because it is forces are very less. Inexpensive cutting tool materials, you can go for normal tools because the material is in soft condition. The higher material removal rate, you can go for higher depth of cut and feed also, and reduces tendency for vibration because workpiece now no more a brittle and very hard, it is ductile in nature. That's why you understand now the machinability is improved. If I want to cut directly ceramic, I need diamond tool, which is costly. At the same time, hardness ratio is very low because if I want to cut a ceramic to the another CBN or diamond, hardness ratio is very low. So forces are very high, tool life is low, and the tool cost is very expensive, and material removal rate you cannot go for very higher, and vibrations and chatter also comes. So if at all I have a simple solution like heating, for example, if somebody want to do on soft some of the small ceramics, you can go using, there is some papers on hot machining like oxyacetylene gas flame you can use, and you can cut with the carbide. Okay, you can use that technology also because your oxyacetylene flame goes around 3000 degrees temperature. Okay, so you can look into it how you can make the process easy. Okay, thermal aspects of machining, what I want to show you is why we are going for the thermal aspects of machining. Okay, if you see the thermal aspects of machining, already I have shown you. Just watch the video. If you watch the video, see lot of fire or chips with red color chips are moving in the machining region, that is just going away. So you can understand how much heat is generated, what are the thermal aspects are going on during the machining operation. If you see the chip, red chip is accumulating there. Okay, you can see in this area, you clearly see the chips are accumulating in the machining region, which are very red hot chips. So the thermal aspects plays a major role. Now you can see that continuous chip in red color is accumulating there and going off after some time. So now you can understand what is the temperature generation, how the heat is affected there, and all those things. You can see now the Okay, energy dissipated in the machining is converted into the three zones, that is called heat in shearing zone and heat in chip tool interface, that is this region. This is called the shearing zone. This is called chip tool interface. Another one is tool workpiece, this region. This is the, as in all metalworking where the plastic deformation involves, energy dissipated in the cutting tool converted to heat, which in turn raises the temperature. Okay. So, because of the severe plastic deformation, normally the heat is generated. Now, heat dissipated, which is in terms of which raises the heat, raises the temperature in the machining region. There is two things. One is heat generation, at the same time heat distribution. During the machining of metal, considerable heat is generated, which converts the mechanical energy takes place. This occurs in the following distinct regions. So, normally the heat is generated 80 to 85% in the primary shear zone and 15 to 20% in the chip tool interface and 1 to 3%, sometimes it will be 5% also in the tool workpiece interfaces. Okay. This is the generation of the heat. Okay. So, normally the distribution, if you see the distribution and all those things, so here it is not there, but however I will explain you the distribution. Normally 80 to 85% will be taken by the chip. This is the, whatever you are showing in the figure is temperature generation or the heat generation. So, how the distribution, normally chip will take 80 to 85%, the tool or cutting tool will normally take around 10 to 15%. So, the workpiece takes around 1 to 5%. Okay. This is the combination of these things will take place. This is nothing but temperature distribution. This is temperature generation. This is temperature distribution. Okay. So, there is a slightly difference is there. In temperature generation, it is the interfaces or the shearing zones. Here distribution, normally distribution, I have given apple to Ram. That means that I am giving to individual entity, that is nothing but this one. So, I am saying individually how the distribution, they will distribute the aspects. Okay. The sources of heat generation in the machining, the shear zone where the heat is generated due to plastic deformation. This is about the plastic deformation where I said 80 to 85% is generated. Chip tool interface where the heat is generated due to frictional rubbing between the rake face and the tool chip. Okay. So, the second one which is because of the frictional rubbing. The third one, tool work interface where the flank surface will rub against the workpiece, which leads to 1 to 3%. Normally, I said already it is fine. About 80-85% of the heat is generated in the shearing zone, while 15 to 20% and about this one already we have seen this one. Adverse effect of the temperature rise. Normally, the major disadvantages are, what are the affecting things whenever there is a temperature rise, that is lowers the strength, hardness and stiffness and wear resistance of the tool. That means that thermal softening of the tool takes place, because whenever I am cutting, so my chip is continuously moving, however my tool is static. That means that continuously the heat is going in, because of which thermal aspects of will takes place and the thermal softening of the tool takes place. That increases the temperature within the tool, which lowers the strength of the tool, hardness of the tool also and stiffness of the tool and wear resistance, and will all go down. Okay. Causes uneven dimensional changes. Whenever the temperature is very high, what will happen? Workpieces also may have tendency to increase its dimensions by nanometers or sometimes in micrometers also, whenever the thermal conductivity of the workpiece material is very high. Induce thermal damage and metallurgical changes to the machine surface. Normally, whenever the cutting tool machining region is very high, what will happen? As you see, the thermal layers will form. There are thermal layers, there are 3 thermal layers. One is, if you see in the EDM process or laser beam process, where is the thermal machining processes, heat affected zone, recast layer and conversion layers. I am not saying that all these layers will form, but there is a chances of these layers, that is recast layer or heat affected zone and conversion layer. Okay, there is a chance, very less chances there, but because the temperature is going up. Okay, so the mean temperature in the turning process is normally in the turning process of the lathe is function of cutting velocity and feed, and A and B are the coefficients. Okay, so the cutting velocity V and tool feed is nothing but this one. For the carbides, approximately A and B values are 0.2 and B is 0.125. High speed steel, normally these values goes up because the thermal softening of this material is faster than compared to the hard carbide tool. That's why 0.5 and B. Okay, so also note that the relation shows the increase in temperature with the increase in cutting speed and feed. Okay, so if the cutting speed increases and the feed increases, if the workpiece is softer, in that circumstances my temperature goes up. Okay, if you see the cutting speed and the energy percentage, normally tool is upper side the workpiece and the chip. Okay, so this is the dissipation. So now we have to measure this temperature. How to measure the temperature? That is called, one is the thermocouple techniques, infrared spectroscopy, radiation pyrometers and all those things. However, just I will tell you processes how experimentally we can measure. Okay, the thermocouple techniques, normally here thermocouple form the junction. See, if you see, if at all I want to cut the orthogonal cutting, normally the best thing is just you take a tube and you take the perfectly the tool and you cut it. Okay, so here you can see the tube is taken, this is the hollow one. Okay, so tube and I am cutting here. Now I am having a junction here because connection is not shown properly. So this is one connection, another one connection is given here. Okay, so this is also connected. So what I mean to say is, I am cutting orthogonal machining process where one junction is on the tool, another junction is here. So there is, whenever I am cutting, this will become hot junction and this is the cold junction, where I am having a disc here which is connected. Basically the headstock will have a hollow structure where I can put a rod which is connecting to the workpiece, and I am connecting this rod with a disc. This is a disc, basically this is disc which is dipped in a mercury. This is, you can see here, this is the mercury. This is called my hot junction, this is called my cold junction, which is connected to this one. So using the Seebeck effect, if there is a temperature difference, then EMF will produce. That is called EMF is generated, which is measured as the temperature. Normally EMF is generated because of there is difference in temperature. This is called cold junction. This is called hot junction. When there is a cold junction, hot junction is converted, then EMF will produce. From the EMF, you can calculate the, by using some relations, you can calculate the temperature measured and all those things. Okay, so the Seebeck effect, back effect will be there. So hot junction and cold junction, you can connect and you can get it. This is what the thermocouples technique. And another one is infrared photography techniques, where if you are machining infrared using this one, so you can see the temperature regions using the colors that are captured in the infrared. Okay, temperature distribution in the cutting zone from the infrared. So normally the temperature, highest temperature will be recorded in the chip tool interface, even though the highest energy heat is generated in the shearing zone, temperature highest is recorded here, because the chip is taking 80 to 85% of heat and the tool is taking 10 to 15%. Here workpiece is taking 1 to 5%. Okay. At the same time, the noting point that you have to see is my chip is continuously moving body. So it continuously moving body, at the same time my workpiece is stationary. Okay. So that means that my continuously chip, what is taking the heat, is moving on the rake surface of my tool. At the same time, it is imparting continuously. Okay. So it is imparting continuously the heat, and it is also rubbing here, because of which normally the temperature recorded in this region will be very high. So that is why the temperature in this region is very high, because of the friction, at the same time because of the chip that is having highest temperature moving on the rake surface. Okay. The another technique is, this is the technique which is employed by the booth rod. These are the some of the things. So these are the two techniques which I am going discuss, that is thermocouple technique, infrared, pyrometers also used, some other techniques also used. Okay. So that about the temperature measurements in the machining operation. Summary of this class, if you see the surface roughness in machining, we have studied factors affecting surface roughness. We have seen a fishbone diagram where lot of conditions are there. Surface morphology and surface metallurgy, how to check, scanning electron microscopy, where backscattered image is there, secondary electron image is there, X-rays are there to elemental diagnosis, what are the elements, and backscattered is used for phase analysis. Experimental ways of measuring the surface integrity, what just now I told. Techniques to measure the surface roughness, we have seen in the previous class, profilometers and all those things. Material removal rate in machining, we have seen now, MRR equal to, what are the equation and all those things. Machinability, simple to complex materials, ductile material, and machinability rating. Then we have seen the laser assisted machining, that is called thermal assisted machining, and all those things. That's all about today's class. Pictures are taken from the internet. I am always saying that from my first class to the last class, it is for the teaching purpose only. For better understanding of the students, I am taking these pictures. So acknowledgement goes to the Google from where I am taking these pictures. Thank you.